So let me stop there and hand over the stage to Phil, who's actually going to walk you through the MirrorWeb story. He's going to tell you about how they went about building the search architecture and what are the lessons and insights that they gained. Over to you, Phil.
Thanks, Chris. Right, so you've probably never heard of MirrorWeb, so I'll tell you a little bit about what we do. We provide web and social media archiving to public sectors and to regulated industries, so financial sector, FINRA regulated industries, and in the UK we've got similar regulations. But what we're going to talk about today is the public archive, the web archive that we've done for the UK and national archives. And this is a publicly viewable archive available online. We also run the UK Parliament Web Archive, which is using similar technologies. But what we're going to talk about is the actual job we did to ingest all of the data for the UK Government Web Archive. So a quick rundown of what web archives are. I don't know if many of you are familiar with the Internet Archive and the Wayback Machine. Well, that's essentially what this is. Website data is stored in an ISO standard WARC format file, and it needs to be indexed to be recovered and playback. I'm not going to go into details about what CDX indexing is, but the reason I need to talk about it is to explain how we did the indexing later. And so, what a CDX index is a list of all of the assets within the web archive, which would be HTML data, PDFs, and anything that was on that particular website. So we create an index, and that creates a text index of every asset in the file. So what is the UK Government Web Archive? Well, it's 20 years of historic archives. It's 120 terabytes of data. And we've got over 4,800 sites archived. A lot of these sites have been shut down and are no longer on the public web, but they're in our archive. We also archive UK government Twitter accounts and YouTube videos. So the UK Web Archive project, we won the tender last November to take this, to move this archive from its previous supplier, which was stored in data centers in Paris. And we needed to collect the data and move it into Amazon. Now, we were lucky that the data had already moved to the National Archives, but it was stored on 72 2-terabyte hard drives. And I had to go there with 2 snowballs and 2 machines that I built that we were able to connect 8 drives at once and ingest the data as fast as we possibly could onto the 2 snowballs, but it still took 2 weeks. The next phase of the project, we had to develop a public-facing website that was capable of serving over 75 million visitors a month. We had to provide full replay of all the archives, like the Wayback Machine, and then we had to do full-text search across the entire archive. The first 3 bits we were quite familiar with all of our financial clients, but we didn't provide at that time full-text search, and so we had a bit of learning to do. So, indexing 120 terabytes of web archives. The web archives are all stored in 100 megabyte files, and they were all stored in S3. We had to filter down the content so that the search only provided results for government domains. Web crawlers traditionally kind of can spread off onto the internet and archive and pull down lots of stuff. We didn't want those returning in the search results. Only certain MIME types were in scope, so we only indexed text content, documents. We didn't index any video, we didn't index any images at this stage. The dataset also contained many, many duplicate pages, and we had a requirement that we were not to provide any duplicate results. So, choosing the search technology, there was 2 choices that we looked at that were popular at the time, Solr and Elasticsearch. Elasticsearch was the winner, as we've seen from the slides previously. It's very popular at the moment, but also Amazon offered us an Elasticsearch service. And we were a small team, and we didn't have a lot of search experience, so it made sense to have a look at running it on Amazon. We chose the Elasticsearch service for a number of reasons. Being able to scale was incredibly important. As you'll see later, we spun up a very large cluster to do the initial ingest and then scaled it back down to an affordable level when we went live. By using their service as well, it meant that I didn't have to employ lots of Elasticsearch experts to run an Elasticsearch cluster, which did help. Managing the access rights to Elasticsearch can be managed by IAM, and that's integrated into the Amazon environment nicely. And we monitor it with CloudWatch and provide alerting along with all of our other alerts. And finally, failed nodes are replaced automatically. I don't have to worry quite as much about it as I would if we were running it ourselves. So traditional tools for indexing, we've got Hadoop and Spark. Now, there are a number of open source projects on the internet for indexing web archives, but none of them actually pushed into Elasticsearch. So we were forced to look at writing our own. And the benchmark was set by the British Library. They run the UK Web Archive, and the UK Web Archive is UK domains, but not the government ones. So they set a record just around the time we were writing our software of ingesting 10 million records per hour. So we set that as our benchmark. Now, what I wanted to do with the ingest job was to take the data stored in S3, process it with EMR through a filter stage, then do an extract stage where we then extracted the full text search from the documents that were in scope, and then we pushed that into the Elasticsearch. We didn't have experience of Hadoop, so we hired a Hadoop contractor, and they quoted us for 1 to 2 weeks of work to move this data into Elasticsearch. However, 2 weeks later, they told us it's going to take 6 to 8 weeks. Why is this? And it turned out we didn't realize that while Hadoop is great for batch data processing on small amounts of large files, this is the small file problem. We had 1.2 million 100 megabyte files, and not only that, they were gzip chunks files. So we had to move the whole data set from S3 into the HDFS to process it. We couldn't read directly from S3 just because the nature of each file had to be uncompressed. And with a WARC, we only want certain parts of it to be extracted. We don't need the whole file if we've filtered it down. So we decided to think outside the box, and some smart members of our dev team came up with what we call WarpPipe, which was, in a way, a rewrite of Hadoop for the cloud. So what is WarpPipe? What did it allow us to do? It allowed us to run incredibly quickly and do the ingest at speeds that are unheard of. Each worker in WarpPipe was able to access the data directly from S3 for the filter stage, and then was able to, we didn't have to move the data, so each worker had direct access to S3, and we were able to go, and we were able to scale the cluster on the fly as well. So what do we actually do with WarpPipe? The data was stored in S3. We used 350 Amazon EC2 instances to do the filtering stage, and we were able to filter the files without reading the actual the WARCs. We did it with the CDX files. The CDX files contained a list of everything, every asset in the file. It just didn't contain the actual full text data. So we knew the MIME type, we knew the location, so we filtered down on the CDX files. Then the next stage, we had 650 Amazon EC2 spot instances that were doing the extract, and they could then take a chunk of the actual WARC data directly from S3 without us having to move the whole file. And then we pushed into Amazon Elasticsearch. Running that many boxes, though, did present some difficulties, and we managed to kill Elasticsearch many times until we got the scale right. So how do we optimize it? I ran a 9-node ES cluster with R4 4x large instances, giving us 144 cores across the cluster. I set the sharding to be 1 shard per CPU. To be honest, it was a bit of a guess, and it worked. But the first few times, we took it out when we had smaller and we had less shards. I had no replica shards for the ingest because that slows things down. And then we used the bulk ingest API of our Elasticsearch to chunk the data in. I think we chunked it into 2 meg chunks. So once the extract workers got up to 2 megs, we pushed that into Elasticsearch. So what was the result? It was fast, very, very fast. We managed to index 1.4 billion documents in 10 hours. And that was averaging 146 million documents an hour. It actually went quicker at times, but that was the average over the length of the time that we did it. And that meant that we didn't have to spend too much on the EC2 instances, and the Elasticsearch cluster that was quite large wasn't too expensive because we only ran it for the 10 hours. We also had this requirement to deduplicate, and we achieved deduplication by creating the Elasticsearch ID as an MD5 char of this string here, which every single asset in a WARC file has an MD5 digest generated, but it doesn't include the URL. So you might have a document that's in many different locations on different URLs, but it'll still have the same digest. So we created a unique digest and set that as the Elasticsearch ID. And what we did is we actually did push 1.4 billion documents into Elasticsearch, but we overwrote them. It was a very quick and crude way that actually worked very efficiently. So we indexed 1.4 billion documents, and then with this deduplication, we ended up with 333 million unique documents in Elasticsearch. It worked quite well. So this had an effect of reducing the index size from an expected about 8 terabytes. We inherited the previous supplier's index, and that was 8 terabytes, albeit that was in Lucene. And we got it down to 2.9 terabytes. And that's quite important because running such a large Elasticsearch cluster, the costs do go up as you add. You have to, I think the maximum drive size that we could get was 1.5 terabytes. So our current cluster is running 1.5 terabytes per node. So running at 144 shards wasn't something I wanted to do in production. And so we actually used the ES Shrink Index API to reduce the shards down from 144 down to 12. And that creates a copy of the index with the smaller shards, and then you remove the old one. And then we downgraded the cluster. This was one of the features of Amazon Elasticsearch. We were able to shrink the cluster down, and it managed it all down to 6 R4 X large instances. And then we have 3 M3 large master nodes. And then finally, we added a replica index to improve speed and redundancy. So what was the cost? Well, 10 hours of R4X large, 1,000 of them would have cost around $2,960. As it was, we didn't use 1,000 for the entire time because once the filter stage had completed, we were able to shut those down. But I ended up with a spot purchase price of $187. Phenomenal reduction. And then the large Elasticsearch cluster that we ran, looking back through our bill, we used it for 136 hours, and that cost us $237, which all in all was pretty cheap. So what did we learn? Well, I learned you can take down Elasticsearch very easily with 1,000 servers hitting it. And I think we'd 3 attempts before we got it right. And obviously tuning the index for indexing is really important. And one interesting thing you might not have realized, there is a 40 terabyte limit on EBS volumes. And we were running quite large volumes on all of these nodes, and we couldn't work out why we were booting up all these spot purchases. They were arriving on, they were showing us booting up and then immediately closing down again, and it turned out that we'd hit this limit. So that's, if you're ever doing anything at that scale, make sure you get your Amazon limits increased. And then, yeah, spot purchasing can save loads of money. So, concluding statistics, what did we end up with? We ended up with 93% faster than the UK Web Archive's Hadoop cluster. Obviously, we got a 70% reduction in cost with the use of spot purchases and 60% reduction in the index size due to deduplication. And that saved us a lot of money, that deduplication. Because if we had to run an 8 terabyte cluster with undeduplicated, it would have been very expensive. So I think I've gone a bit fast there. I do apologize, it's my first reinvent, but I'm sure we can do some Q&A.
Yep, sure. So, well, thanks, Phil. I think last bit, some closing thoughts. So as you've seen, there's a lot of flexibility that Elasticsearch offers, and Phil has already shared some cool insights in terms of how he has optimized it. especially with Spot instances and how he's handled ingestion of smarter way, and also with Elasticsearch, how he gained a lot of new insights as he actually went about doing it, especially with shrinking the indexes and actually saving money on that. Hopefully this session was super enriching to all of you, and I think we'll be around here anyway for Q&A. So stick around, if we can actually take all the questions offline, more than happy to answer them for you. Thank you so much.
Thank you.